In this video, we are going to learn how to create slope fields. This is a picture of the behavior of solutions to a differential equation. So the idea is that we create an image in the xy plane, which allows us to ascertain the qualitative behavior of solutions to a given differential equation. We can tell when it goes up, when it goes down, that sort of thing. Slope fields are also called direction fields. There's a little bit of different language here, but it's all referring to the same idea. So imagine that we have a first order differential equation of the form dy dx equals something on the right hand side, might have x, might have y, might only have one of the two. That's okay. I'm going to summarize all the possible right hand sides with the expression f of x and y. So this is just whatever dy dx is equal to. Imagine that we had a picture of a solution to such an equation. So say this curve is a solution, maybe the solution to an initial value problem with this differential equation. What we could do is along this curve, sketch little pictures of tangent lines. So take this curve now and imagine that I'm sketching little tangent lines at different points along this curve. The slope of each of those tangent lines is dy dx. Or in other words, if I pick one of these points and plug that point into the function f of x and y, it's the value of that function at that point. So dy dx gives us a way to find the slopes of these tangent lines. The idea with slope fields or direction fields is to go the other direction. Imagine that I don't yet have the curve, but I do have this differential equation. So at different points x, y, I could plug x and y into the right-hand side of this differential equation to get out a number. That number represents the slope of the line tangent to a solution at that point. So with direction fields, what we do is we sketch these like little tiny line segments where the slope of each of these little line segments is the value of f at that point where we're anchoring that little line segment. So it's like start with the slopes, and then with the slopes, see if you can kind of fill in an idea of what the curve that solves this differential equation and passes through that point would look like. So this will become clearer with examples. So let's go on to the first example. Okay, for this first example, let's consider this autonomous first order differential equation dy dx equals y. Notice here the right-hand side, what I called f of x and y in the previous slide, is just y. So f of x and y is just y. That tells us that if we were to pick any point in this xy plane here and try to find the little line segment that we need to graph in order to generate a picture of the slope field, we're just looking at the y coordinate. So let's do this for different values of y. Okay, starting along the x-axis here, y is 0. It's going to be a little bit hard to see because I've got an axis there, but if you can tell what I'm about to do, everywhere along the x-axis, let's sketch a little line segment of slope 0. So flat, if you can't see it, distinguish it from the axis, just trust that it's there. Now let's go up 1 unit to y equals 1. Everywhere in the xy plane where the y coordinate is 1, the little slope that we need is that value of y. So every single point along the line y equals 1 is going to have a little slope of 1. Now I could sketch like tons and tons of line segments, but that's not typically what we do when we generate a picture of a slope field. We just do enough to give a representative idea of what the behavior in the xy plane looks like. So let me add some little line segments where y equals 1. Now let's go up to y equals 2. Everywhere along the line y equals 2, the little slope that I'm going to draw is slope 2. Go up one more, it's slope 3, and et cetera, et cetera. If you wanted to, you could also fill in sort of intermediary values. So they don't just have to be whole number values of the coordinates. I could do at 1.5, all of the little slopes I sketch have slope 1.5. So really, you want to imagine that every single possible xy coordinate in the xy plane has an associated value. It's just that we don't do all that because it would be impossible to see it. We just give enough little line segments in order to give like the big picture. Down below the axis, when y is -1, -2, -3, -4, we draw corresponding slopes going downwards because there the slope is negative. Okay, so at the end of the day, this is a picture of the slope field for this differential equation dy dx equals y. Now, with this picture, we can give a feeling or an idea of what solutions to this differential equation look like. So starting with, uh, let's say y of 0 is 0, we know that these are flat. So that's actually an equilibrium solution for this differential equation. If y is ever 0, it's going to stay 0 forever. If you go up to positive values of y, what we're actually looking at here is the exponential growth model. So if you were to just pick like a random point on this picture and then kind of imagine progressing in a way that follows the direction that the slopes are pushing you, you start to generate curves that look like this. Same story down below the x-axis. If I just imagine kind of throwing confetti onto this picture and then letting them evolve, we follow the behavior of solutions to this differential equation by following the way that these slopes are pushing us. For our second example, let's look at the differential equation dp dt equals zero point 0.4 times the quantity 1 minus p divided by 40 times p. This is a famous differential equation called the logistic model. Here, zero point 0.4 and 40 are parameters. So you might look at a logistic model where that leading term and also that denominator 40 are different, but that's okay. It's still a logistic model. P is like population over time here. So in this picture, I'm focusing on P greater than or equal to 0, although I will include a negative value of P just to give the complete picture. This is a model which is used for a very specific scenario for a population, and I think we will be able to describe what that scenario is after we've generated the slope field. So what we're going to do is take different points in the TP plane, plug them into the right-hand side of this differential equation to get the slope for a little tiny line segment that we will then sketch at this point. Once again, this is an autonomous differential equation, which means the right-hand side only depends on P. We don't see the independent variable T over on the right-hand side. So ultimately, what I'm going to do is just pick different values of P, compute the slope, and then stretch that to the right because there's no T dependence on the right-hand side of this differential equation. Okay, so let's do this. I've worked out these numbers out loud, so I'm gonna just kind of indicate different values of P and then let the slopes appear on this picture. We start with P equals 0. Notice that because of that last term, if you plug P equals 0 into the right-hand side of this differential equation, you get dp dt equals 0. So that means that it can be hard to see, but along the t-axis are little line segments which are flat, they're horizontal. It makes sense if you think about a population. It's like if you don't have the population, then you just never have the population. So P equals 0 is an equilibrium solution for the logistic model. You might recognize now that we've described equilibrium solutions twice in this video, that an equilibrium solution occurs whenever you see a horizontal line emerge on your phase space, or rather your slope field. Okay, what happens if P equals 5? If I take the number 5 and plug it in for P in the right-hand side of this differential equation, we have 0 point 0.4 times 1 minus 5 divided by 40 times 5. Again, I worked that out ahead of schedule, so that's 1.75, which means that all to the right here, we're going to sketch as many line segments as we need in order to describe the behavior, the motion of a solution that would be passing through the value P equals 5 as having a rate of change of 1.75. Okay, that was a wordy way of saying we draw little line segments with slope 1.75. Let's go up now to P equals 10. If you plug 10 in for P on the right-hand side of this differential equation, you get 3. So again, I'm going to draw a family of little line segments of slope 3, and it's a little steeper than it was at 5. We're going to go a little bit steeper again. If you plug in P equals 15, you get 3.75. So all of these line segments have slope 3.75. Go up a little bit more to 20. If you plug 20 in for P on the right-hand side of this differential equation, we have slope 4. I want to make a remark here, which is that I'm generating this picture with a computer, so my slopes here are pretty accurate. However, if you're doing this by hand, you don't have to agonize about 1.75 versus 3 versus 3.75 versus 4. You want to give the idea. So don't spend too much time trying to make a slope exactly 1.75. Just trying to realize the overall behavior here. It's going up It's getting a little steeper and steeper as we go from 5 to 20, and make your slopes model that behavior. I'm just saying this because, like, if you do it with a computer, yes, it should be accurate, but if you're doing it by hand, you just wanna give the behavior. You don't want to spend too much time trying to make your slopes exactly accurate. So just give the idea of what's happening here with the slopes. If we go up to 25, we're actually going to have the same value that we had at 15. So when p is 25, the slope is 3.75 again. That pattern continues. If we go to 30, it's the same as when it was 10. So that's slope 3. 35 is going to be slope 1.75. And then when p equals 40, if I plug 40 into the right-hand side of my differential equation, because of that middle expression, 1 minus p divided by 40, if you plug in p equals 40, it turns into 1 minus 1. So once again, we have a family of horizontal tangent lines at the value p equals 40. So that tells us that p equals 40 is another equilibrium solution. Let me go up just one more level to 45. When p equals 45, if you plug 45 into the right-hand side of this differential equation, you're actually going to get a negative slope. So here, p equals 45 gives you slopes that look like negative 2.25. And that's actually also what you see down here if p is negative 5. So let's see, negative 5. And at this point, I think we've done enough to be able to describe the behavior of a population which is modeled by this logistic differential equation. So what happens if the population is 0, stays 0 forever? If I don't have any iguanas in this room, I just never will. Likewise, if your population is 40, it actually stays 40 forever. So 40 is another equilibrium solution, which is greater than 0. So that's like if I had exactly 40 iguanas. If you look down here, and this is something that's easier to see perhaps with an image generated by a computer. If you look at low values of population, if you just zoom in right here, you might look at this and start to think it's exponential growth. If you just saw this part of the picture, you'd think, hey, this population is growing exponentially. But actually what happens is there's like an inflection that happens here at 20, that's half 40. So we're growing, growing, and then we sort of inflect. It's like the concavity changes. And then the growth rates slow down so that we level off towards 40 for any population sitting between 0 and 40. So they grow, but they kind of slow down and approach 40 as t goes to infinity. On the other hand, if a population is bigger than 40, if we're above 40, if you plug in any such number into this differential equation, you're going to get a negative slope. So if you're above 40, then you go down and you approach 40 as time goes to infinity. So actually, the logistic model is often used for a nice simple equation for a population which has a carrying capacity. For this value here, 40 that I've chosen for this denominator, the carrying capacity for this population would be 40 individuals. So this gives us a nice picture of how solutions to the logistic model behave. Again, I want you to focus on the qualitative aspects, the idea that we grow, we kind of inflect, we slow down, the long-term behavior, rather than focusing too hard on the actual numbers here. So focus more on what this communicates to you about how solutions to this differential equation behave. In this example, we have a non-autonomous first-order differential equation. So here we're looking at the equation y prime equals x plus y. We could think of this as, instead of y prime, dy dx equals x plus y, where the right side of this equation is going to give us the slopes at each pairing of points x and y. So what I'm going to do now is first just take this differential equation and add some little line segments to this graph over on the left in order to start to generate a slope field. You will see that that feels like kind of proceeding one by one in order to generate the slope field. So then we'll bring in the notion of isoclines in order to give you a way to perhaps more rapidly fill up your slope field. Okay, so let's start by just picking a few points, x and y, in this xy plane, plugging them into the right-hand side of the equation to get the corresponding slope that we would like to sketch for our little line segment. Start at the origin. If x and y are both 0, then 0 plus 0 is 0. Once again, it's going to be hard to see, but let me add a little line segment at the origin with slope 0. Let's go now 1 unit over to the point 1, 0. So 1 plus 0, the x plus y coordinate for that point, is 1. So at the point 1, 0, I'm going to sketch a little line segment of slope 1. Similarly, if we come up 1 unit to the point 0, 1, now we're looking at a slope of 0 plus 1. So once again here, at that point, I'm going to put a little line segment with slope 1. Let's go left and down. If we're over at -1, 0, that's -1 plus 0. So here, the slope is -1. And likewise, down 1 unit on the y-axis, we have 0 plus -1. So we have another little line segment with slope -1. And we can keep doing this. So you have different ways that you might try to grab points and plug them into the right-hand side of this differential equation. You could sort of spiral around like I did. You could focus on the first quadrant, then the second quadrant, third quadrant, fourth quadrant. My next option might be to grab the point 1, 1. So here in the first quadrant, plug 1 plus 1 into the right-hand side of this differential equation, and we get slope 2. So that's somewhat uh, not, I don't want to say tedious, but it just involves kind of checking a lot of points one at a time. So let's talk about isoclines. So first, what is an isocline? An isocline is a curve in the xy plane along which this right-hand side all has the same value. So if I name this right-hand side f of x and y, then we can say that an isocline is a curve in the xy plane on which f of x and y, the right-hand side of our differential equation, is some constant value. The idea is that if I can figure out what my isoclines look like, then if I take an isocline, it gives me a whole curve on this picture, along which I know all of the slopes. They would all have the same slope. So let's see what the isoclines look like for this example. We have that f of x and y should be some constant value along each isocline. That means x plus y is a constant. That's a straight line. If you prefer to see it in maybe more traditional notation, you could write this as y equals -x plus c. I've given you here the general form for each isocline for this differential equation. What I'm going to do now is add isoclines to this graph one at a time. So let me identify the isocline along which dy dx is always 0. So that's like saying the right-hand side of this differential equation is 0. Uh, that's like saying that this function f of x and y needs to be a constant 0. If you come down to the form that we've put this in, we're looking at the straight line through the origin with slope -1. So the isocline along which our differential equation always takes the value 0 on the right-hand side looks like this straight line. I know that every point that lives on this line in the xy plane satisfies that when I plug it into this differential equation on the right-hand side, the x coordinate plus the y coordinate is 0. Consequently, I can go ahead and add a bunch of little line segments to the slope field. Given this line, I can just add some line segments which are flat. So all of these little line segments have slope 0. Notice that includes the origin, the point that we already identified. This isocline here is not really part of the slope field. This is like a tool that I'm using in order to generate these line segments. So I could remove it, and you see that this is the kind of picture that we're looking for. But just for the sake of illustrating how to use isoclines, let me add that isocline back. Now let's look at a different isocline. Let me imagine that I want to identify all of the points in the xy plane that give me a right-hand side here of value 1. That's like saying that f of x and y is 1, which means that all of those points live on the line y equals negative x plus 1. If we graph that line, I can now rather quickly add a bunch of line segments to this line, which all have slope 1. So now we have the 0 isocline and the 1 isocline, if you will. Similarly, if we go up to having a right-hand side of 2, then we're looking at the line y equals negative x plus 2. Let's add that. Every point along this line, when plugged into this differential equation, gives us a right-hand side of 2. So for my slope field, I can go through this line now and add some representative line segments, all of which have slope 2. And we could keep going, but let's kind of go down and identify that if I'm looking for a right-hand side of negative 1, that's like saying y equals negative x minus 1. If we add that to our graph, I can now say, hey, all of the points on this line give us a right-hand side of negative 1. So we add a bunch of little line segments which are going down with slope negative 1. Similarly, we could have all of the points which give us a right-hand side of negative 2. And once we've identified that they all live on this line, the line y equals negative x minus 2, we can add a bunch of little line segments, all of which have slope negative 2. So let me take away these isoclines now and show you the picture that we're left with. It's kind of at an angle because of the shape of the lines, but that's okay. So the idea with these isoclines is instead of trying to plug in points one at a time and getting out slopes and just adding them one at a time, we get to add a whole family of points all at the same time. So I could say, hey, this whole line, I've done all the work for every single point on this line, and now I can add a bunch of line segments. So that's the usefulness of isoclines as a tool for generating slope fields. Let's look at one more example. Okay, let's finish this lesson with this example. We have the differential equation y prime equals cosine of x times y. Like the previous example, this is a non-autonomous differential equation because we have x dependence. So y prime is the cosine of the product of x times y. We are going to jump immediately into using isoclines in order to generate or try to generate a nice slope field for this differential equation. Now, I'm going to warn you that we are going to go through the process where we will sketch a few isoclines and add little line segments along those isoclines. But honestly, the picture is going to get pretty busy pretty quickly, and it's not going to look that good by the end of it. However, I still want to show you the process. So I wanted to give you a little bit of variety compared with the previous example. So that's why I picked y prime equals cosine of x times y. So what we'll do is we'll do the best we can by hand. And then at the end, I will put up probably a nicer picture generating the slope field with a computer. Okay, so we have cosine of x times y is the right-hand side of our differential equation. So what we've been calling f of x and y is cosine of the product of x and y. To find the isoclines for this differential equation, we're looking for curves in the xy plane along which cosine of the x coordinate times the y coordinate is the same constant value. Cosine is a periodic function, so what I'm going to do is just identify a few key angles that we might plug into the cosine function. We will add isoclines associated with those angles, and then we will essentially stop there. We'll get an idea of what the slope field looks like before we put up a better picture, which just fills in some extra information. Okay, so what I'm going to do is only pick a few key angles off of the unit circle. So let me actually sketch the unit circle. How about I sketch it here? Okay, I'm going to try to draw a circle. This is pretty good. Okay, this is supposed to be the unit circle. We have a lot of angles on the unit circle that I can plug into the cosine function and get a nice convenient output. So we have 0, pi over 6, pi over 4, pi over 3, pi over 2, et cetera, et cetera. I'm not going to even plug all of those into cosine. I'm going to start with 0. So we will look first for a curve so that x times y is 0. Then we will go to pi over 2, then pi, then 3 pi over 2, and then 2 pi. That'll be some of the isoclines. Then we'll rotate the other direction. So we'll go to negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. So those are going to be the angles that we find isoclines for. Okay, so let's start with x times y is 0, this first key angle. So our first isocline that I'm going to add, or isoclines rather, that I'm going to add to this picture are going to be associated with xy equals 0, putting us here on the unit circle. That means that cosine of any xy pairing that satisfies that x times y is 0 is going to give us 1. So that's the slope that we'll associate with these isoclines. If x times y equals 0, that means either x is 0 or y is 0. In other words, the x-axis is an isocline. And so I can take the entire x-axis and add some representative little line segments to it, all of which have slope 1. And then likewise, the y-axis is also an isocline, so we'll do the same thing there. There. So we've got two isoclines, the x-axis and the y-axis. Let's go next to pi over 2. If I solve for y, if you'd rather see this in the form y equals a function of x, that tells us that y is pi over 2 divided by x. I'm going to write it that way. 1 over x is your classic hyperbola shape. This is just pi over 2 times that. So here's the shape of the graph of all points in the xy plane, which satisfy that y equals pi over 2 divided by x. So we have these curves in the first and third quadrant. Those are isoclines. What is the slope that we associate with those isoclines? Well, if we plug in xy equals pi over 2 into the cosine function, the cosine of pi over 2 is 0. So to these isoclines, I'm going to add little line segments, all of which have a slope which is 0, so they're flat. Okay, so that's the start of our picture. It's just going to get a little busier. Let's go around now to pi. This is very similar. It's just a different numerator. So if xy equals pi, then that means y equals pi over x. Okay, so this is just another hyperbola shape in the first and third quadrants. And in fact, now you can basically deduce that for any following equation we're going to write down, it's going to have a similar shape. So we have these for positive angles, hyperbola in the first and third quadrants. Okay, when we have x times y equal to pi, cosine of pi is -1. So to this new graph, I'm going to associate little line segments of slope -1. Let's go to pi over 2 now. Oh, sorry, did I say pi over 2? I meant 3 pi over 2. Again, it's just a different hyperbola, and the picture gets pretty busy. So let's add that. And to this, this pair of isoclines, we're going to add little line segments whose slope is 0 again, because cosine of 3 pi over 2 is 0. And then let's finish this counterclockwise rotation around at 2 pi. So we started at 0, then I did pi over 2, then pi, then 3 pi over 2, and now we're back to 2 pi. That's going to be, if I can fit it here, xy equals pi means y is pi over x. Okay, so I'll add that to the picture. And now we've cycled all the way back around to a place where the cosine of x times y is 1. So again, to these isoclines, we'll associate little line segments which have slope 1. Okay, this gives us an idea of what the slope field looks like, at least in the first and third quadrants. Now, I only picked a few angles because I knew this picture was going to get pretty crowded pretty quickly. But if you wanted to see the intermediary behavior between 1 and 0 for the slopes. You could pick some of the other angles that sit between 0 and pi over 2, likewise in the other quadrants if you wanted to fill in what looks kind of like missing space in this picture. Let me pause here, and I want you to think about what would happen, what kind of isoclines we would be looking at if instead of rotating counterclockwise in the usual way, we then went the other direction. So now I'm going to start back at 0. We've already got the axes here, so we won't generate new isoclines for that angle. And rotate clockwise. When we rotate clockwise, we go from 0 to negative pi over 2. So see if you want to go all the way around again, maybe the same key angles, but this time in the clockwise direction. Okay, let's go once around the unit circle in the clockwise direction. I'm not going to erase what I already have. I'm just going to throw negatives in front of everything. So if xy equals 0, we're back to the case that we already addressed. That's the axes. If x times y is negative pi over 2, so I've rotated down here clockwise, then the only difference is that we're looking at the hyperbola y equals negative pi over 2 divided by x. And it's the same shape as what we already saw, except it's in the second and fourth quadrant. So that's what the negative does to the graph of any hyperbola. So we're flipping into the second and fourth quadrants. And along y equals negative pi over 2 divided by x, we're at a place where the cosine function is 0. So on this new pair of isoclines, I'm going to draw a bunch of little line segments which have slope 0. Let's rotate around now to pi. If x times y is negative pi, then we're looking at y equals negative pi over x in the second and fourth quadrants. And on these isoclines, the cosine value is negative 1. Keep going all the way around. Negative 3 pi over 2 is up here. So x times y equals negative 3 pi over 2 is going to give us this pair of isoclines. So y equals negative 3 pi over 2 divided by x. And again, we're at a place on the unit circle. We're at an angle where the cosine function is 0. So we add some flat little line segments to this set of isoclines. And then we're almost done. Let's rotate all the way around to negative 2 pi, which is back here to where we started. Did I skip something? Oh, here, when I wrote pi, I should have written 2 pi. My apologies. Let me see if I can just fix that. Okay, originally it should have read 2 pi, 2 pi. That was our first trip around the unit circle. Now we're going clockwise around in the unit circle, and we're going to finish on negative 2 pi. So we have the graph of y equals negative 2 pi divided by x. And at negative 2 pi, we've rotated back around here where the cosine function returns you the value 1. So to this final set of isoclines, we're going to sketch little line segments of slope 1. Okay, it's not the best picture in the world. So I generated this with a computer, but there's a lot going on here and here because of the stretching of these isoclines, the slopes get a bit spaced out. So it looks like there's somehow like it's emptier up here and it's really not. That's just how I graphed this on the computer. But at least looking at this picture, if I take away the isoclines to see it a little better, you can see that we have this kind of like radiating outward shape. It's going to be periodic, of course, because the cosine function is periodic. So we expect this sort of rippling shape to continue as we travel outwards from the origin. This is the right thought process to graph this slope field with isoclines. Again, you can add in a little bit more detail by picking more possible pairings of x and y than the ones that I identified. But having gone through this process by hand now, let me step aside and let you finish doing anything that you'd like to do by hand. And then I'm going to put up a picture that I also generated with the computer, but just filling in a lot more of the detail so that you can get a really good idea for what the slope field for this differential equation looks like.